my name is Jose, and in collaboration with Sergio Pastrana, we have made this SoK on privacy-preserving computation techniques for deep learning. In this work, we have analyzed over 30 state-of-the-art contributions. Our goal was to understand how cryptographic techniques to compute privately can be applied to deep learning. For that, we have analyzed the different tools and techniques that authors have proposed. We aim to evaluate the efficiency and usability of the different proposals and to understand future lines of research in this area. This is an overall view of the paper. First, to protect deep learning, we need to understand which are the privacy benefits we want to obtain from it. Once we know the goals, we can detail the different cryptographic mechanisms that ensure partially or totally these goals. Some authors purposely introduce modifications to the use of the mechanisms in what we name protocols to ensure more privacy guarantees. To start, I would like to give you a glimpse of what deep learning is and how we use deep learning nowadays. Deep learning is a set of statistical models which are able to learn from datasets. In this work, we focus on supervised learning, that is, when we learn from datasets where we know the expected input and output of the dataset. Deep learning is carried out into phases. First, we make a training phase, where we extract correlations from the labeled datasets into a model. Then, we can use the extracted correlations in order to predict on unseen data. The main building blocks of deep learning models are called layers, which are usually executed sequentially. Authors have proposed different types of layers over time, which adapt to different characteristics of the data. However, for this work and the techniques we're going to describe, we will work with two main kinds of layers, which are linear layers and nonlinear layers, and their main difference is whether they can be simplified into a polynomial or not. In short, both linear layers, dense and convolutional, can be simplified into matrix multiplications, and thus multiplications and additions. However, the problem comes with nonlinear layers, which are the magic of deep learning. They introduce changes that are needed to learn complex patterns. Here, we propose the max pooling and the activation functions, which are used for forward propagation. However, for training, the problem comes with loss functions and their derivatives of the activation and max pooling layers, which are also nonlinear. Now, I would like to comment on why these works are crucial. The ability of deep learning to correlate apparently unrelated data allows solving problems in many disciplines such as finance, social sciences, or healthcare. Now, we need to understand that these works are dealing with private data, and we need ways to protect it. First, we need to protect the inference and training data. Also, the deep learning models are private information that should be protected. Finally, we need to understand how to keep legal and other intellectual property issues. We have identified three main privacy guarantees that classical deep learning models do not always achieve. Input privacy relates to the input elements of a deep learning model, that is, the training dataset and the inference samples. We have to protect that from unauthorized third-party access. Output privacy relates to the security of the output elements of deep learning, that is, the trained model and the output classification. When deep learning models find a statistical distribution outliers, they often overfit and somehow memorize the classifications of these samples. Various attacks permit retrieving this information. By using certain privacy-preserving techniques, we can protect the data from these attacks. There is a final consideration that we have identified through analyzing the different works, which is model secrecy. People invest money and time into creating deep learning models, and releasing it to a third party could be losing the intellectual property. Furthermore, if certain output privacy guarantees cannot be ensured, it is better to have access control over the model. In this case, we divide it into architectural secrecy and weight secrecy. Architectural secrecy refers to not releasing the specific organization of the layers, and weight secrecy refers to not releasing the specific weights learned during training. Having understood the different privacy goals of deep learning, we can make a classification of privacy-preserving techniques. I would like to start with data privacy, which is techniques that focus on reducing the amount of information that datasets carry out. In that way, models trained with that data ensure that they will not include private information. Differential privacy is one example of these techniques. Let me jump over privacy-preserving computation techniques and start with trusted execution environments. Trusted execution environments are really common in modern processors. They work by privatizing the memory space of a process. When the information of that process has to be processed, then the information is decrypted in the processor, processed, and re-encrypted again. Strictly speaking, this is not the focus of our work, since the computation is fully done in clear text. Federated learning is a protocol first proposed by Google, over which there have been multiple enhancements. These protocols ensure that the information is kept private on each of the silos or parties participating in the learning. The only information exchanged are the gradients of training, and the central server aggregates them privately. This is a completely different field in which some of the PPCTs that we will describe take part, but in general we will consider a small subset of information being processed privately. And then we go over privacy-preserving computation techniques, where the data is fully obfuscated and an adversary processing it has no knowledge about it. Apart from that, it has cryptographic guarantees behind the protection. Here we overview three types of them. First, we have servomorphic encryption, which is a property of encryption schemes that permits operating over the ciphertext and having these changes applied over the plaintext. As we see in the figure below, the envelope is encrypted on the local premises and sent to the cloud. The cloud in our case would contain the deep learning model, which can privately compute any function over it. Once the cloud has the result, it can be sent back to the client who decrypts it. The cloud would have learned nothing about this process. In the top figure, we show there are various flavors of HE. Out of these, level homomorphic encryption has been the most used in the proposals. That is because it provides a simple but efficient way of computing information, though the circuits are of a limited depth. Recently, we are seeing third-generation schemes with good performance in bootstrapping, so we believe they will become an option in the future. Another privacy-preserving computation technique is secure multi-party computation, which permits a number of different parties to interact and jointly compute functions without revealing their private inputs. In the figure, we can see how the different parties can sort of divide their inputs. In reality, this preprocessing generates a complementary representation of information or sharing. These sharings can be sent to the cloud servers, who operate on them. The individual shares do not reveal any information, and once combined back, reveal the result of operating on the shares of data. The top diagram shows different SMPC protocols that have been used for deep learning. In the advanced constructions, we would find more efficient and secure protocols than these secure variations such as SPDZ. Hybrid techniques are a specific classification we include in this SoK. They are mostly one of the two categories, either SMPC or HE, but they often implement cryptographic conversion protocols which permit switching to other protocols in the different categories. Deep learning is often carried out in floating-point arithmetic. However, many of the activation functions can only be computed through Boolean arithmetics. Through the cryptographic conversion protocols in hybrid techniques, we can also switch the arithmetic. This makes these techniques really powerful for computing deep learning. As we will see, they shift the paradigm in inference. All of these techniques provide input privacy. That is, anything that is input to these processes is kept private and not revealed. Now that we have explored the taxonomy and goals, we can start understanding how the basic protocols that were proposed work. The first modern paper to propose deep learning and privacy was CryptoNets. I say modern because there's another paper, Tasty, which was proposed in 2009. However, at that point, neither HE nor deep learning were mature enough for this. CryptoNets approximated floating-point numbers with integers and was used with power of 2 activation functions. This was not very good, and in 2017, CryptoDL processed improvements to the activation functions by giving it more accurate linear approximations. Other works, such as Faster CryptoNets or Yang et al., propose more optimizations, but more on the deep learning side to accelerate the computations. On a sideline, we have other approaches focused on other arithmetics such as TAPAS or FHE-DINN, who use Boolean and discretized neural networks respectively. On the other side, we have SMPC. All the approaches of SMPC use Boolean circuits for the neural networks. In general, they are faster to the HE counterparts. However, having to use the binary weights makes changes to the neural network which are not very convenient. However, there's a complete shift in the paradigm when Gazelle and Chameleon appear. Instead of modifying the deep learning structures, they propose changes in the cryptographic techniques that permit executing deep learning the same way it would be done classically. With the rise of privacy-preserving deep learning, many of the works focused on bringing usability for data scientists to use these tools. There are 3 main research lines in this timeline. First, we have PySwift and TF Encrypted, who are big open-source initiatives that revolve around creating common interfaces for deep learning and privacy-preserving techniques, but until recently they are mostly used and focused on usability. Other works focus more on the security side, together with the usability, such as ngraph and their successors ngraph2, PlateML, or MP2ML. Apart from that, we have CryptFlow, who focuses on a secure multi-party computation side, and TinyGarble. While all of the previous works require manual parameter selection, Chet and Eva provide simple interfaces that automate the parameter selection. All the previous papers focused on inference, that is, assuming a neural network was already pre-trained. In this timeline, we explore a bit more the side of training. There's a first difference in all the cases. Neural networks need to be much simpler. Training is already a very cost-ineffective process, considering we add a complex layer on top of it, which is the cryptographic primitive. It makes it very difficult for this process to be carried out. First, it works on HE preparing an encrypted dataset, and then they train a neural network out of it. That is the case when a server receives an encrypted dataset and trains a model out of it. Even though they manage to do that, the comparison in resource consumption is very poor. In the case of SMPC and hybrid techniques, the scenario is very similar to siloed federated learning, but when all operations, even the forward propagation, are performed encrypted. In that case, it permits outsourcing the training to an external server and also keeping the data secret. All these papers make something different than the rest, so I encourage you to look at the paper if you're interested in it. Now that we have covered all the papers, I would like to highlight some takeaways of the different contributions. First, we will cover security and then efficiency and usability. There are two kinds of adversaries when designing a protocol. The honest but curious adversary is a passive adversary that complies with the protocol, but tries to learn as much as possible from the interactions. The malicious adversary, on the other hand, has stronger capabilities, as it can tamper with the protocol, dynamically changing the inputs, or interrupting the participation at any point. Although there are ways to enhance the honest but curious adversaries to malicious, it is often computationally costly, and most of the articles we have seen propose a honest but curious adversary. In the highlighted column of the table, you can see how most of the papers use a honest but curious adversary. We believe it is interesting for the future to start understanding the adaptations of the honest but curious into the malicious adversary in an efficient way. While we claim that most protocols preserve architectural and with secrecy, it is because the paper's model owners are considered a trusted third party that will not steal the model. We believe the consideration of model secrecy could be enhanced through the use of PPCTs in combination with trusted execution environments. As we see on the table, except in training proposals, most of the papers cover architectural and with secrecy. We believe it is necessary to introduce output privacy in these protocols. In the table, the blue hyphen means that the guarantee depends on the specific implementation, so it is left aside from the protocol. Most protocols ensure input privacy, but output privacy depends on the relationships between the actors and the way models have been trained. End-to-end pipelines, including all these techniques, are the future of privacy-preserving deep learning. As a final security takeaway, we believe there are attacks such as model extraction or model inversion attacks that can be uncovered by the use of PPCTs. Although it may be far, we need to envision future intrusion detection systems that detect authors trying to exploit these attacks against models. Privacy-preserving processing will require envisioning a new generation of countermeasures to attacks. It is difficult to compare efficiency in the different works. Each work trains on a different neural network architecture and obtains different weights. Different deep learning trainings may result in different base accuracies, and its translation to the privacy-preserving protocol may be affected differently. We believe it is needed to standardize the benchmarking. While the difference in computational architectures may not be easy to quantify, we believe it is feasible to elaborate common models for the community to be able to objectively compare efficiencies. To analyze usability and reproducibility of the many works we covered, we tried to understand the maturity level of the contribution until reaching data scientists. For that, we searched for the open and source implementation of the protocols. If it was available, we have compared the implementation with what was proposed in the paper. Furthermore, we checked if the repositories are maintained and if they implement a bridge to common deep learning frameworks. In inference, many works are released open source. All of the open implementation match the article proposal and they immensely favor reproducibility. In training proposals, there's much less code sharing. We believe it is due to the performance limitations. Finally, in usability-focused proposal, the code sharing is really good, and most proposals are well maintained and there are relevant updates for the code. We see some common flaws, and we believe integration within standard frameworks would also help the goal of having common benchmarking. Furthermore, we believe common points and integration with common deep learning frameworks are steps forward towards compatibility with data science communities. If you want more information of the code repositories, the list is in the article. Finally, I would like to give some concluding remarks. We believe PPCTs are on its way to reach data scientists, and more usable solutions will be approaching. The security and privacy innovations make using privacy a really good alternative for deep learning, and PPCTs are a good provision of security and efficiency, especially for inference. We believe there are many evolving technologies, and this favors the creation of many new proposals. One of them, Falcon, is presented next in this conference. Thank you very much for listening to me. I'll leave here my interest and current research lines. If any one of you wants to drop a mail, I'm happy to answer. There you have all the references for the different works. And said that, I remain at your disposal for any further questions you may have. If you were not able to submit any question during the conference, I'm happy to answer it by mail too.